Okay.
So I have a mix of stuff to try to talk about today. I'm not sure that ever works because we always get caught on one topic, but I do have a mix of stuff to talk about. And it's partially because we've been having a mix of stuff we've been talking about in the email in the last couple of days. I guess the mix, maybe the mix is between roughly two things: the special commutative Frobenius algebras on the one hand, and on the other hand, this question you've been asking me about two rigs and how to sort of present or sketch certain two rigs and things like that, which I think of as, to a great extent, falling under the belief method. So that's sort of the two topics here. So
did the stuff about the art and reciprocity go away?
No. That's the Frobenius algebra stuff.
Oh, okay. Great.
I mean, it's under that heading, and we're supposed to talk about all sorts of different things today, but we'll see how it goes.
Okay.
Right, terrible danger always if I'm starting out with the most unimportant topic, but I'm going to try that right now because I'm not going to spend a lot of time on it. Just going to start out with the most unimportant topic. So we talk about special commutative Frobenius algebras. I have various puzzles about them. Puzzles for torturing myself, puzzles for torturing you, et cetera, et cetera, et cetera. So one I've been torturing myself with, or has been torturing me, is so you've certainly suggested the intuition that special commutative Frobenius algebras, or more generally special commutative Frobenius commutative monoids, or tensor monoids, special commutative Frobenius tensor monoids in some nice context, are morally supposed to be like finite sets. They're supposed to be sort of like what happens to the concept of finite set within the context that you're working in, or something like that. You've certainly given me that impression, right?
Yep.
But I'm, torturing myself with this finiteness stuff, for example. So, I think I've been making some stupid mistakes, and maybe I just want to present a little bit of me correcting one of my stupid mistakes. So I kept on imagining that I could come up with much more infinitary special commutative Frobenius algebras. And I kept on thinking that if I take something like infinite sums of the finite ones, or infinite products of the finite ones, or something like that, that I could cook up some sort of, even working over a field, let's say working over the complex numbers or something like that. Like a nice algebraically closed field like the complex numbers. I thought that I could trick myself into thinking that I could construct some very infinite, infinite flavored special commutative Frobenius algebras, which didn't seem like they would deserve, the title of honorary finite sets. I mean, sometimes you do think of infinite sets as honorary finite sets, but that's not going on in this game, I think. So I'm just going to mention one example where I thought to myself, oh, okay, maybe I can get a really big, infinite flavored special commutative Frobenius algebra in this way. And I tried it, and then I was pleasantly surprised when I saw that it didn't seem like it would work. So let me try to give my example here, okay?
Yep.
Or counterexample, or not, it's like a failed example, or what? So I'm going to write down I guess a presentation of a commutative ring or something like that. So let's say we're working over the complex numbers, and I'm going to take an infinite sequence of generators. Sorry, I'm agonizing over whether I should start with 0 or 1. I guess I'll start with 1.
Okay.
And then I'll put in certain relations. So first of all, I'll make them all idempotent. So aj squared equals aj. And then I'll make them like distinct pairwise. They multiply out to 0 or something like that. So aj times a.
People say orthogonal sometimes, but yep.
Orthogonal in that context?
Yeah.
It's kind of suggestive, but this is for j not equal to k. And is that all I want? I guess, unless I've forgotten something, that's all I want. And
yeah, this is a very good doomed attempt.
Well, but I really like the spectacular crash that I got particularly when I tried to draw it geometrically, the way you've been talking about in this upcoming or already published blog post that you're talking about. So, so basically, I think this is, I mean, one way you can think about this is that this is really a Boolean algebra that's been glorified into a commutative ring. You know, there's some sort of adjoint functor. You can take the underlying Boolean algebra of a commutative ring by taking the idempotents. And you can just freely left adjoint do the opposite of that. And we're kind of doing that to this Boolean algebra here. I think, if I'm not too badly screwed up. And so I think what we've basically got here, if you think in terms of the spectrum of this, as you know, it's the spectrum of a commutative ring, but you can also think of it as the spectrum of a Boolean algebra. Spectrum of Boolean algebra is basically a totally disconnected, compact, totally disconnected topological space, or something like that. Something very much like that. And
I don't know if you need to say Hausdorff. Maybe that
totally disconnected.
That.
Totally disconnected sounds like it's encouraging it to be.
Yeah.
So I mean,
I'm resisting saying I should have resisted saying that.
No, you shouldn't have resisted saying because now it gives me a chance to say, hey, well, right, maybe there is a danger.
No, that's why I should have resisted saying it.
But it gives me a chance to say that maybe I didn't mention this to you, but you know, when I began to get the idea of what you were trying to say about special commutative Frobenius algebras, I mean, there were several moments when I got better ideas of what you were trying to say about it. But there was one moment when I suddenly thought to myself, oh, that's why they call it separability, because separability is in some sense the ultimate separation condition. Like, you know, what is your part of Hausdorffness? But it's related to this other thing, totally disconnectedness. That's related in some way too.
Yeah.
So, and of course, I'm not sure it's the ultimate separation condition. Maybe there's some other even stronger separation condition, but that's the way I think of it at now. So
there is, yeah, I mean, yeah, I mean, if you look at like Wikipedia under like totally disconnected space,
yeah,
you see that there are actually like a couple of different notions. There's one that's probably the main one, which is the one you're trying to use here, that makes the connection to Boolean algebras hold. But you could argue,
is it possible that, you know, these shades coalesce when it's compact or something like that? I don't know.
I don't know, but anyway, I'll just mention that like discreteness is in some sense the ultimate separation.
Sure.
Yeah, and you're sort of getting very close to that, but definitely not there yet when you say when you talk about these stone spaces. So
right. But the separable ones, like the separable Boolean ring or something like that. I have to think about how that terminology works, but I think it works okay. Those are really read, but they're also finite, perhaps. Let's see.
Okay, let's see how this crashes and burns then.
Sure. So, so part of the point is that as a totally disconnected compact, right, maybe people do say sometimes totally disconnected compact Hausdorff space. Maybe I've heard that phrase, but anyway, it is Hausdorff. But my definition is really that it's the spectrum of a boolean algebra or something like that. It's really just a boolean algebra in disguise. So it's like this particular one, the spectrum is the 1-point compactification of the counting numbers. If you think about it. How does that work? Maybe the extra 1 point is when they're all 0 or something like that? When all the values take the value 0? What?
I don't know. I don't.
Doesn't that look like it's going to give a point to the spectrum if all the variables take the value 0? You know, they're all going to be idempotent. They're all going to be pairwise multiplying out to 0.
Yeah, I guess so. Okay.
And that's the 1 point of the 1-point compactification. That's the actual, you know, the only other things you're going to get are by setting one of the variables to 1 and all the others to 0. So as soon as you set one of them to 1, you have to set them all to 0. And you can only set any one of them to either 0 or 1 because they have to be idempotent. So I'm talking about,
as soon as you set one of them to 1, you have to set them all to 0. You have to set all the rest to 0.
All the rest to 0. Yeah.
Yep. Okay. Yep. That's a good argument. Yep.
And you know, that's for classical models over like complex numbers or any reasonable field or anything like that. So well, let's just look at this example. So well, so first of all, we've got this, you know, my rough intuition, and maybe it turns out to be actually the correct statement, but it started out as my rough intuition, was that being special commutative, for a commutative ring or commutative algebra to be special Frobenius would mean that that the well, so I'm thinking of it as an affine scheme now. So I'm thinking geometrically. So it's not an affine scheme, and I can talk about the diagonal subscheme. And basically it's the property that subscheme can have, as property of the scheme that we're talking about, the original scheme, that that this diagonal subscheme has a Boolean complement subscheme. And once that has a Boolean complement subscheme, then you can define a function, and in fact, an idempotent function, by just putting, you know, on each component, when it's, you know, separated into Boolean separation into components here, you just put ones on each component, ones or zeros on each component. So you put 1 on the diagonal and 0 off the diagonal. And that seems to behave a lot like this, what I'm calling the cotrace of a special Frobenius commutative algebra.
What is cotrace?
You know, it's kind of like the trace thing, except dualized. So so how do you do it? It's, you know, it's this thing from, maybe it's this thing that goes from the tensor unit to the tensor square. And, you know, it's very cup-like or cap-like or something.
Okay.
So the dual of that, don't you sometimes call that thing the trace or something like that? I mean, it seems very trace-like in a way.
I would never call that other thing the trace. I'd
Okay.
call it like a pairing or something like that.
Pairing. Okay. Okay.
But I get what you mean.
So that, okay, this is the co-pairing. Yeah, this is that co-pairing. So I'm trying to draw the Cartesian product. Cartesian product, because geometrically the Cartesian product is corresponding to the tensor product of
Hold on a second. Sorry.
Go ahead.
Okay.
So I'm trying to draw the Cartesian product of the 1-point compactification of the counting numbers, or whatever you call them. So I'm making some progress. I just have to keep on doing an infinite amount of work to get the picture finished. So you can kind of see, oops, that's not bad. You're doing this right. Are you getting the idea here of what the...
You're bunching them up, yep.
And, I think my really first offhand, stupid, naive intuition said, that the diagonal is kind of separated from everything else. And it isn't. Right? Am I doing it right now? Maybe I should try to put in the diagonal in a different color here. And you can see how unseparated the diagonal is from the off diagonal.
So you'd look at that last point in the diagonal.
Yeah.
This point at infinity.
Yeah. And
that's the one that you can sneak up on from off the diagonal.
Yes. So this is sort of propaganda for the idea that maybe it really is true. So for example, maybe it really is true that over the complex numbers, every special commutative Frobenius algebra is really just, a finite set. A finite so is that true? Do you know if that's true? Is that obvious from what?
Yeah, that's true. I mean, so
it's just a finite Cartesian path. Well, actually, how do we say this? You've got.
I'd say it's the algebra of functions on a finite set, but
okay, yeah, that's perfectly good. Algebra of complex valued functions on a finite set. Yeah.
So one thing you can do is you can show that for any Frobenius algebra has to be finite dimensional.
You just mean over a field.
Over a field. Yeah, sorry.
Yes.
There's probably something like that for other rings, but I haven't thought about that yet.
Sure, but I'm just saying that,
you're trying to.
Yeah. Okay. Yeah. No, I'm not even quite prepared to. But I was thinking of, what if you take a Frobenius algebra over a Cartesian product of an infinite number of. But yeah, even that, I'm not sure. Yeah, I'm not sure. So
I bet it has to be a finitely generated projective module over, if you do a Frobenius algebra over a commutative ring, because it has a kind of inner product on it. I don't know that for sure.
Yeah,
but
yes, but the inner product, the inner product could be valued in this commutative ring that is itself functions on an infinite space.
Sure.
I was imagining some weird case, like you could do it, like if you're working in comodules over an infinite thing, then you're saying that each fiber is finite, but they could increase in dimension without bound. So I mean that's not exactly an example because it would be using comodules rather than comodules of a coalgebra rather than modules of. But anyway, so yeah, okay. So this is good enough for now. That was supposed to be the unimportant thing. Now I'm trying to get to more fun stuff. But it is, I don't know. I just like the idea that this picture actually helped me understand, and this picture is a version or another variation on those pictures you were drawing in the blog post.
Yeah, it is, and I almost feel like including this one, but it's too much work to draw. So
sure. What do you mean? Is that a joke?
No, I just meant it purely.
Oh, it actually is. Even part of it is too much to draw, or too much work. Okay, so all right. So now I mentioned another puzzle at some point about special commutative Frobenius algebras, and that was classifying them over the integers. And I asked about this in email. And have you thought about it more? I mean, when I asked you an email, I forget what you said, what you replied, but you said something like, well, first of all, there's the classification over the rationals. And that's a lot of work involving Galois theory and stuff like that. And so you said, you know, that might be a start on the problem of classifying them over the integers. But did you think about it at all more about what the...
No, I'm afraid not. No, I didn't.
All right, so I still don't know, but I have a guess. I mean, I should know because it seems easy enough to figure out from what I'm claiming, but you know, maybe I screwed up somewhere. So my guess is that it's kind of the same classification as over the complex numbers.
That boring?
What?
That boring?
That's my guess. Because isn't there this famous thing about, you know, maybe I could be totally misremembering. I could be totally misremembering. But every what is it? Every algebraic extension of the rationals is ramified somewhere, something like that. Am I misquoting that? Coming close to quoting it correctly?
I don't know this stuff very well, but it sounds right to me.
And so that ramification is, I think, kind of obstructing this Frobenius co-pairing from existing. So I mean, okay, let's do an example here, okay? So you can try to see what's going on. Let's try the Gaussian integers. Okay. Mm-hmm. So now, I mean, we've talked about how to make the Gaussian rationals into a special commutative Frobenius algebra over the rationals.
Mm-hmm.
And let's see, now that was when I was thinking in terms of the pairing, and I think what am I trying to say? The pairing is the sum of the number with its complex conjugate or something. No, did I say that? Well, yeah, I mean, if you're thinking of, yeah, I mean, you can talk about, I can get away with talking about complex conjugate, I guess, when I'm talking about Gaussian rationals. But, you know, it's just it's also the conjugate in a Galois theory sense or something like that.
I think by pairing, you now mean what I'd call a co-unit, a thing of one that eats one argument.
Okay, maybe I screwed up. Let me think. Right, I said pairing, and that might have been the wrong thing to say. So co-unit, is that right? It sounds like you're right, but let me just try to orient myself to.
I'm actually.
Yeah.
I'm confused, but anyway. That's at least a linear thing. What you said.
Yeah. No, I think you're right. I think I just got screwed up for a moment. I okay, a little disoriented, but I think that's right. So yeah. Well, but then what would the pairing be then? The pairing would be sorry, no, maybe no, I'm still disoriented. So
I think the pairing would be like the real part. I mean, what do you describe as like twice the real part? So I think the pairing would be like twice the real part of the product of two elements. Because you can always get the pairing by first doing multiplication and then doing this co-unit. First you multiply and then you cap it off.
so what so what are you saying? Let's see. Sorry, I'm just disoriented. So okay. So the thing I'm talking about goes from okay. Okay, I guess you're right. Okay. Sure. Oh, okay, yes. I was totally disoriented. I think I'm less disoriented right now. Okay, right. And the pairing is just take the product and then you apply that co-unit. That's what you probably just told me. But now I actually see it, I think. Okay, sorry, I was just disoriented. And so then, yeah, okay. So right. So what are we saying for the pairing this time? The pairing is just the twice the real part of the product or something like that. Is that what you're telling me?
Yes.
Twice the real part of the product. That would be the pairing. And you're okay with calling that the pairing. Did you have a name for that thing ever?
That's the closest I've ever had to a name for it. Yeah.
Okay. So okay, but then we're trying to think about what the co-pairing would be. And it probably would be, it would be a good exercise to really work this out, not just for the Gaussian integers, but for all these other quadratic number fields, the algebraic integers in there. But in this example, I'm hoping we can sort of convince ourselves that the co-pairing would end up with factor of 1/2 in it. I think I did actually. I couldn't reproduce the calculation right now, but I think you might be able to see almost. I mean, there's probably really easy ways of doing the calculation, but I think you can almost see, just because of the factor of 2, there's sort of a factor of twice the real part, that when you do the co-pairing, you're going to get a factor of 1/2, which means that the co-pairing doesn't exist. That's what I think. Hope I'm not screwing up here. I think I'm claiming that because you can sort of write down for what the formula should be for the co-pairing on the and you see this elsewhere, right? I mean, you see it in the co-unit or whatever way you have of generating the whole operations of the theory. It's going to fail. There's going to be factors of 1/2 or something like that in there that are going to make it ill-defined. And that's because, morally, geometrically, we have this ramification, which is like a branch point. So it's like, not a covering space. It's not, right? It's got this point, this prime 2 of the spectrum, where the fiber is not what it should be. It's, So, yeah.
You're making it sound like that 2 is not just coming from the fact that it's a quadratic extension of the.
Well, right. I mean, these are, you're asking excessively good questions. I don't want you to ask good questions.
Because I don't really see exactly where that 2 is coming. I can believe there's a half somewhere, but I don't actually see where.
Well, I think what happens is that I didn't get far enough to check this, so I can't give you a good answer to your good question. But the typical thing is that, what am I trying to say? I think it is like every quadratic number field, or a whole bunch of quadratic number fields, right? A whole bunch of quadratic number fields are ramified over 2 because of the quadraticness. But then I think there are some that aren't ramified over 2.
Oh, cool. I don't know anything about that. I should. It sounds really fun, but I don't.
Well, we might be getting close to looking at that, but probably not right this second.
Yeah.
But in addition,
anyway,
what?
Anyway, I think I get your point. That's sort of surprising to me, but makes sense in retrospect.
Well, yeah, but I just wanted to say that, with these other, like, the square root of 5 instead of the square root of -1 or something like that. But the square root of 5, you're probably going to get ramification at 5 as well. Or if you don't, right? It's apparently, if the theorem is true, as we seem to be remembering it, that all the extensions are ramified somewhere. And I'm hoping that they're, not just ramified at like the infinite prime, but they're actually ramified at some finite prime. And you know what I mean? So it's like a lump in the carpet, you can chase it around, but I don't think you can ever get rid of it. I think that's what the theorem is saying. That, there are no totally unramified extensions. Is that the right word? Totally unramified? I don't know. There are no unramified extensions of the rations. I'm hoping you are get the point, as you claim that you are more or less getting the point. But what is the point of the point? The point of the point is that this is supposed to be propaganda for the idea that if right? I mean, so this classification problem turned out to be really easy. Right? It was no worse. What?
Sorry, let me try to pause.
Go ahead.
Okay.
Okay, now I have to remember where we were. Where were we? So, sorry. Can you just? I just did a bad job of.
One of the funny things. Yeah. Okay. Yeah. Okay. So I mean, it's interesting because
where are we back on now?
Frobenius algebras are.
We're back on now. We're recording. Is that right?
Yeah. One of the things is that the commutative separable Frobenius algebra stuff. It does handle ramified extensions, because you're supposed to get the whole Galois group in terms of.
No, but that's only if you're working over the field.
Right.
Yes. Okay. Yeah. Sorry. Yes.
So I mean, you might.
Right, and yeah.
You've almost been like fooling me into thinking that like this separable Frobenius algebra stuff is only supposed to be an algebraic way of describing ordinary coverings, but it can handle branched coverings.
No, but the way it handles branch coverings is by killing the bad guy. Right? I mean, it can handle. Right, the way it works, like with actual branch coverings of the Riemann sphere, is that you're not dealing with the Riemann sphere. You're dealing with this voodoo Riemann sphere.
Right. Yeah.
All of the points have been removed.
Yep. Yep.
Yes.
Anyway, it's interesting that you're saying that over the So if over the integers you don't.
Yeah.
You don't do that for some reason because you're not converting anything.
I mean, so first of all, I am less sure. I mean, I think, right? I think we are less sure. You and me are less sure about what happens over a non-field than over a field. We've heard theorems stated about the case over a field, and we may have looked up cases over a commutative ring, but they have annoying fine print in them sometimes, or something like that. So, we're kind of faking it here when we're going beyond the field case, but that's okay. And because we're exploring, we can see what's happened. And so yeah, right. I am suggesting this philosophy that if I understand what you're saying, that that the whole program, the whole Frobenius algebra idea should, it's way too interesting to only waste on fields. We should really apply it to commutative rings, and keeping in mind this sort of voodoo interpretation of the relationship between spectrums of fields and spectrums of commutative rings. That every time you invert something, you're just removing from the spectrum the places where that thing is zero. And so in a field, you've removed all the points from the spectrum, except for this, non-standard generic point, which is just, really the identity morphism of the field. So, so that's my mental picture. I've said this before. We said this before. My mental picture of the spectrum of the rational numbers is this ultimate pincushion version of the Riemann sphere, ultimate voodoo pincushion, where you got the Riemann sphere, but all the points have been removed.
Individual.
Still something left. It's like, and I also think of it as like a Cheshire cat type thing. What's left is a generic point. It's sort of like the smile of the Cheshire cat.
Yeah.
But that's all nice story, but we're trying to see how this story plays out in this actual context. So what I was starting to say was that the point of the puzzle about the classification over the classification of the special commutative, classification of the special Frobenius things over the or special commutative Frobenius things over the integers is that the classification turned out to be really easy. You couldn't have any of these Galois type extensions. And the fact that it's easy in that way, which could seem disappointing at first, but it's actually not disappointing. The fact that the classification is so easy over the integers encourages us to think that that we'll also get a relatively tractable, manageable problem if we just kind of don't go so wild with the voodoo needle. Just remove a few points and see what's going to go on. See what's going to happen. So an example would be, let me just give it a silly example here. So let's take so let's see, my screen is visible here. I can draw stuff.
Yep.
And let's say the integers. So you can see where I'm drawing that. The integers adjoin. So we're killing off the prime 3. And we're killing off the prime 7. And so we could take as a goal, well, I mean, right, we're trying to encourage ourselves to believe that we have some manageable goals here. But as usual, I have, a bunch of fallback things. So one goal would be to classify all of the special commutative Frobenius algebras over this thing. So I don't know, let's call this A or something like that. Right, so we're probably supposed to get a boolean topos or something like that from this, which is supposed to be sort of like the representations of the profinite fundamental group or something like that. Yeah, right. There's probably some language where to make that actually make sense, you're supposed to say something like profinite étal fundamental group or something like that. But that terminology doesn't especially mean anything to me yet. But right? We're just we don't have to worry about such technical things. We can just go ahead and see what happens.
Yep, sure.
So we can try to do this. We could try to understand this. But if this turns out to be too hard, then there's other things we could do, right? We could try to sort of, in some sense, abelianize this profinite fundamental group. Or right, just try to understand the universal abelian coarsening of this. And that's getting really close to art and reciprocity and stuff like that. And so, I think it's actually really interesting to think about what happens if we don't impose the abelianist condition. But I don't have anything terribly interesting to say about that yet. Just that I think it will really be interesting. Which
I would just say something really.
What?
I would guess something really silly, which is that they're like, you expect that the fundamental group of just really.
Sure, very naively.
Anyway, it would just expect it to be like the free group on two generators or the profinite free.
Yeah, we've certainly speculated that it's like that. Yeah. I mean, but all sorts of funny things could happen that we're not expecting. But that's a very sensible, stupid guess.
So those two generators should have something or others to do with Frobeniuses of 3 and 7.
I have to stop and think about what you mean by Frobenius, right? This is right. My theory about,
Oh no,
there's no mathematician who does more than one thing.
Right. Okay, here it just happened. Yeah, now I finally get to see what Frobeniuses have to do with Frobenius algebras. Right. So for each.
Well, I mean, but I'm not claiming that I understand. I'm not claiming that I understand yet how all Frobenius.
No, I don't understand.
But it's very suggestive. So go ahead, because I'm still not sure. I'm just not sure I'm completely agreeing with you yet. But let me try to understand what you're saying. Go ahead. You're suggesting.
Well, people like to say that, like, well,
I think you might be flipping the two primes that are involved in the reciprocity laws. You might be on the opposite side of the reciprocity law from where I am, but I'm not sure. It sounded like that from what you said. Sorry. Go ahead. Go ahead.
Maybe I'm screwed up. So I mean, okay. I wanted to like figure out what the generators of this fundamental group on two generators might be, and
yes,
they should have something to do with the numbers 3 and 7. And so I may have gotten it.
I mean, what do you mean? What do you mean what they are? What kind of answer are you looking for? What kind of answer would you accept if somebody says, "Oh, this is the generator"? You want them to give it as explicit automorphism of an explicit.
Well,
extension?
That would be great, but I'm thinking that we're going to like see them manifested in these special commutative Frobenius algebras as ways. So I'm thinking of these special commutative Frobenius algebras as like finite set bundles covering spaces.
Yes.
Of some of this mystical
space.
And so for each non-contractible loop in this mystical space, there may be like some standout non-trivial covering space that has a twist as we go around that loop. And so the generators we might just see them indirectly in terms of like special commutative Frobenius algebras where there's something twisty in the 3 and the 7 direction. So twistiness often winds up meaning non-split. so like when you go to a complete field, the only special Frobenius algebras are these boring ones that are just sums of the commutative one. Just sums of copies of the field.
Yes.
But then And so we say that they split over that complete field.
Yes.
But if you're working over a non-complete field, there will be some ones that aren't of that form, but they become of that form when you extend your field. So there could be something like the non-contractible loop having to do with the number 3 will give us some special commutative Frobenius algebra. It involves the number
Well, yeah, I mean,
3 in such a way that like it's not split, because you can only split it if you're able to. Sorry, I probably said it backwards. Yeah, I'm saying
that's okay. There's
yeah. No, I was making it sound like there's a problem at 3, but what there is in some senses is that's weird. Yeah, there's some kind of non-problem at 3 because you are able to invert 3. The problem we ran into was due to not being able to invert.
Yeah, I mean, we're saying that now when you create a special commutative Frobenius algebra, you're allowed to put factors of 3 and 7 in the denominator of the operations.
Right. Yeah.
But yeah, there's a whole bunch of one of the reasons I'm having trouble being completely sure how close to on the right track you are is because there's a whole bunch of dualities going on here. Dualities in some vague sense of duality that confuse me sometimes. I mentioned one that, there are these, reciprocity laws that say, P is a residue mod Q versus vice versa or something like that. And I can get mixed up between the roles of P and Q, particularly because there's reciprocity going on where they switch roles. Mm-hmm. But in addition to that kind of reciprocity duality, there's also this other kind of duality that confuses me that I think you just brought up, which is, I mean, I think I used to think that, what am I trying to say? That I used to think that the way to sort of work your way up to the complicated situations would be to start out with rings that just have very few primes or something like that. But now I'm taking the opposite philosophy, which says that the thing to do is to work your way up to the complicated stuff is start out with the examples where there's just a few primes that are removed, like 3 and 7. They've been removed. And again, one of the dualities that's going on here is that when you remove the primes 3 and 7 from the spectrum, you remove these points of the spectrum with the voodoo needle, you're putting in these reciprocals. And moreover, especially what you're doing is you're beginning to make GL1 more complicated. So like GL1 of the integers starts out very, very simple. Mm-hmm. It's just a Z mod 2, it's just 1 and -1. But as you go through this voodoo localization process, actually, that's right, that's another one of the dualities that confuse. It's actually the same duality, but it's another way of stating what the thing is. People use this word localization when you're inverting something. Uh-huh. And that really confuses me sometimes, or it has confused me many times, because there's this idea of localizing at a prime versus localizing away from a prime. Do you want to invert that prime, or do you want to keep that prime as the only one that you don't invert and invert all the others? Yeah. And when you think of the geometric interpretation of this, it has to do with whether you're just puncturing, just getting rid of that one point, puncturing it, putting a puncture in there, putting in the voodoo needle right there, versus something, right? Sometimes you're localizing at a prime, so you're getting rid of all the other points, and you're just leaving yourself with some little tiny infinitesimal neighborhood of the point that you didn't get rid of.
I think that's what was confusing me. So what happens?
It's so easy for me to get confused about this. Go ahead.
What happens if you take the integers and you localize at 3? What do you get?
localize at free, you get something like, well, again, there's different meanings of localization. I mean, you can, so one of the things you can do is you can just localize in the sense of inverting, yeah, okay, I'm trying to remember, what are you trying to say? You force this to become a local ring. Don't trust me on this, but one of the things you can do is you have a prime ideal, like the prime ideal generated by 3.
Mhm.
And then I want to say something like, you sort of force that to become the unique prime ideal of the thing that you're creating. And I think that means you're inverting everything outside of the ideal or something like that. Yeah, inverting everything outside of the ideal, and that makes the ideal that you started out with the prime ideal, something like that. Let's hope I'm not screwing up too bad. And but the moment you do that, you've now got a very prominent ideal. It's like the only ideal or something like that. And once you've got that, it's you've got the powers of that ideal. So you've got like a filtration or something like that, an algebraic filtration. But one of the things that some people like to do, and there's all sorts of variations on this game, but when you've got this filtration, you can sort of like, what am I trying to say? It gives you like a topology or something like that, and you can complete with respect to that topology, and you can get a stronger, more analytic notion of localization. So, somehow this thing that started out as just algebraic geometry is becoming, maybe it still is algebraic geometry, but it looks kind of like analysis to me, because you're, but right, it's this p-adic type analysis. It's the, what do we call that? Non-Archimedean analysis.
So the first step, do I get the 3-adic integers?
Don't tell me.
They already did, or else I can't anymore.
Yeah. That's. What am I trying to say? There are really good answers to these questions, but I don't have them right on the tip of my tongue.
Mhm.
Yeah, so I'm right. The p-adic integers is in there somewhere, but so is there are all sorts of, let's leave this as an assignment for a future thing. We really want to understand these different kinds of localization, p-adic
Okay, but anyway, I think that
p-adic numbers.
so I think that
Completion of the
p-adic
localization, the uncompletion of the localization. Yeah, what you say? What are you saying?
anyway, I think that reveals my confusion in that if I did the 3-adic integers and other things related to that, like the 3-adic numbers, then somehow the Frobenius involving 3 would play a role. But that's when I was inverting everything except 3.
I think that's right. That
So, and
right.
that's like this business of, yeah. So so here what we're doing is not that at all. Well, forget the 7 for a second. We're inverting 3. And so that should have some.
Right. So I mean, right, this should sort of remind us one of the things that this should sort of remind us a little bit of. It reminds us a little bit of Grothendieck's design d'enfant or something like that. Because right, the whole point there is you're studying branch covers, but you only allow branching at a very few special points that you favor. Like 0, 1, and infinity or something on the Riemann sphere. And by doing that, you're making things very tame. Right? So instead of taking like the field of all meromorphic functions, or even worse, some sort of, what am I trying to say? Is there some like Puiseux expansions, some gigantic field of, what am I trying to say? Yeah, I think there's some giant field of Puiseux, how do you pronounce that? Puiseux expansions that like allows you to get, you've got the voodoo needles at every point or something. Am I still trying to say, I can... Sorry, I'm probably getting myself confused by talking about things I don't really understand very well. But what am I trying to say is right. I was trying to say that you can avoid all those things that I don't understand by just taking, like, the ring of polynomials. Right. You could start with the ring of polynomials in one variable over the complex numbers. And at that point, you've already got one puncture in the Riemann sphere, which is infinity, because infinity isn't really in the spectrum of the polynomial ring. But then you can just put in a few more punctures. You can just throw in, the reciprocal of 1 and the reciprocal of, am I saying this right?
0.
Right. And the reciprocal is 0. What am I trying to say? No, I'm not saying this right. The reciprocal of the thing, no, don't throw in the reciprocal of 1. That's already there. Throw in the reciprocal of the thing whose zeros.
Yeah, z minus 1.
Yeah. So, right. So there's 1 over 1 minus z, and that'll give you a puncture at where?
At 1.
At 1. And just 1 over z, that'll give you a puncture at 0. So you just throw in those two things, and you've now done a little bit of localization, and it's enough to pretend that things that are branched at 0, 1, and infinity are unbranched, because we've killed off the annoying guys who would complain. We've killed off the complainers in the spectrum. So we're doing a version of that game. And right, and that's encouraging too, right? Because that is a fun game to play in the very geometric case. So maybe it's a fun game to play in the and like you were suggesting, right? And in fact, right, and part of the point is, right, maybe this is sort of supposed to be already obvious, but in that geometric case, people end up studying the free group on 2 generators.
Right. Yeah. And there were
or a profinite version of it.
Right.
Yeah. What?
And yeah, one thing I was wondering about is there are really 3 punctures. So I'm wondering about this A here. Does this have 2 punctures, or is there like a 3rd puncture?
Yes, there may be some mysterious 3rd or 4th puncture. I always, people are always throwing in, oh yes, the extra prime, but there's more than one extra prime that people throw at me.
Okay. Yeah,
we're exploring. We don't know what's going on, but
we're getting over our pay grade here.
That's right. So okay. What was I trying to say? So right, I think I have another complaint about something you said. I meant to say it before, but I forgot. It's not a big complaint, but you were suggesting, I was asking, what do you mean by seeing these generators? How explicitly do you want to see them? And you were saying, like, you want to see them, I don't know, acting on Frobenius algebras or something like that. But, right, part of the point is that we really are kind of expecting that you'll be able to have arbitrarily high finite dimensional. Probably, that's a good guess, right? That we'll have arbitrarily high finite dimensional Frobenius algebras in this example. So in any particular Frobenius algebra, you won't see the whole, right? You'll just see some finite coarsening. That you'll see that generator there, but you won't see in its complete refinement, because you don't see the complete refinement of the generator until you take this ideal infinite extension. That's just so somehow that's connected with rumors that I hear people say sometimes, right? People sometimes say, or they said it until recently, I don't know if they still say it, but they said that nobody knows an explicit element of the absolute Galois group or something like that.
Yeah, I think they still say it. Yeah,
they still say that. but they do have weird conjectures about it, right? I don't know.
Yeah, there's a conjecture for what. Well, yeah, there's a conjecture for what the profinite Galois group of the rationals is.
And it is connected with the Grothendieck's design and the Grothendieck-Teichmuller theory or something like that.
That's one way to think. Yeah, there's something about it being like, yeah. Anyway, there's stuff about. Anyway, there's stuff about Lie algebras, describing it using Lie algebras. There's.
Well, but again, that's all part of the fancy version of Grothendieck-Teichmuller theory. You know, when I talk about Grothendieck-Teichmuller theory, I actually usually draw the actual designs, but you know, was it? Who's the guy? The Russian guy who kind of called it the Teichmuller theory. Say it again.
Oh, I don't know. Drinfeld.
Drinfeld, yes, Drinfeld, yes, Drinfeld. So you know.
Yep.
It could be that we're talking about. It could be that you were just talking about some of Drinfeld's ideas, but it could be some of the ideas that he might have called Grothendieck-Teichmuller theory for some strange reason. No, yeah. I don't know.
Yeah, they do. It's connected anyway. They talk about it.
Okay. So right. So we're probably not going to get a finite group out of the, even if we abelianize, we're still probably going to get a profinite group rather than a finite group. But right, so right, I mean, and then maybe that's too annoying to begin with. So we could, we like I say, I have, an infinite series of fallback positions every time I find a problem too difficult. So but that's what Conway said, right? He said it's supposed to be a finite thing or something like that. It's supposed to be well ordered. I'm not sure mine is well ordered. How about if I just try to classify the Z mod 3 torsors here? So that, right, that's a start on understanding the whole Galois. I mean, this would be like, I don't know, maybe it's like taking the Galois group and tensioning with Z mod 3 or something like that. I didn't really think through exactly what it is, but this is some sort of, piecemeal approach. So yeah, so I'm now thinking about classifying the Z mod 3 torsors over this thing. And now we're going to take a really ad hoc approach. Let's try to come up with some reasonable guess for what all the Z mod 3 torsors are going to be over this commutative ring. And we can think of those Z mod 3 torsors as being some kind of special commutative Frobenius algebras with nice Z mod 3 action on them. And right, I mean, this is in the direction of classifying all the special commutative Frobenius algebras, but it's just very special commutative Frobenius algebras, these ones that are actually Z mod 3 torsors. But it's a good start. And in fact, it's not only is a good start, it's actually a really good start. I mean, I think, a big part of what really is there is what we're going to maybe see here as we explore this in an ad hoc way. So let me start taking some stupid ad hoc guesses here, see how far we can get about what the Z mod 3 torsors are going to be here. And as we do this, we're going to really, really try to look at this classification in multiple pictures, multiple viewpoints. And some of the connections between these different viewpoints will be very Artin reciprocity theorem-like. Yeah, we'll but I'm not sure how to say that. So I'm just going to jump in the ad hoc examples here, and then we'll try to see how we're looking at this in different pictures and how the connection between the different pictures is giving us the germ of some important theorems, perhaps. So So first of all, let me try to guess. Well, okay. First of all, I'll ask you. Do you have a guess what the classification of this? Have I made it unambiguous enough now that in principle you understand the question and you could take a stupid guess as to what the classification is going to be?
I don't think I could take a guess.
Yeah.
Partially because when you started doing this over the rationals, you seem to like need to use the Eisenstein.
Yeah, that's going on here. That's going on here. Yeah.
Springboard.
But you use this Eisenstein thing in right. I mean, there are different ways you can do it, and one of the ways you can do it is you sort of treat the Eisenstein integers formally, treat the Eisenstein quantity formally, and I think that's a big part of what's going on here. I mean, well, we'll see how it goes, but you're using that as an excuse for not taking much of a guess here.
Yeah, I can just barely understand that stuff before we.
Okay. Right. I can sympathize with you because I've been presenting it in such a bizarre way. But what we're doing now is supposed to, after today, you're supposed to have much, if we manage to do it without too much screw up, then after today, we're supposed to have a much better intuitive picture of what this classification really is. And not only would we have a better picture of what the classification is, but we'll really see it as a classification. It's not just playing around with the partial classification, but this is going to be the classification of all the Z mod 3 torsions over this special ring, which is designed to be somewhat tame. So it's got, a very slightly interesting GL1. That it's got.
Okay, well, let's see it.
Okay. So you're not going to take a guess. That's the classification. I'm going to tell you my guess. Is that right?
Yep. Yeah.
All right. I'm guessing, if I'm not screwing up too badly, I'm guessing that there's going to be 9. 9 of them, and they're going to be arranged in a in a 2-dimensional vector space over the 3-element field. And let me also mention, as we anticipate doing more ad hoc stuff, but having it get less ad hoc as we proceed. Another flavor of example that I really want to look at very soon would be, instead of taking the integers with just a few voodoo nicks introduced, is I want to take like the Gaussian integers with just a few voodoo nicks introduced into the spectrum and stuff like that. But back to this example. So yeah, that's what I think it's going to be. So let me see if I can. There's various things we can do here. Let's try taking GL1 of a tensor. So how does this work? I guess we try the Eisenstein integers now. Is that how it works? I'm not sure I understand how to do this. We're going to take that thing. And then I guess we're going to tensor with the 3-element field. And then we're going
to tensor a group with a field. I guess an algebraic group.
Well, it's a GL1. It's no. This is not supposed to be an algebraic group. I mean, I'm not at the moment. I'm doing things ad hoc, so I'm not sure what I'm doing. But at the moment, it seems like I'm.
Oh, it's an abelian.
Unlike usual, I'm treating this right. The fact that it's got the second slot filled in means that it's not really an algebraic group anymore. It's an actual group now.
Okay.
So, but it's an abelian group.
Yep.
And
okay. So yeah, no,
it's a Z module.
Yeah, I get it now. So okay. I can try to figure out what it is.
Okay. And it has an involution on it, which is, I guess I don't know what to call it. For the moment, I'll call it the Eisenstein thing.
Uh-huh.
So, this is an involution.
Uh-huh.
So this is an involution, a linear, it's a linear operator, but an involution, involutive, whatever, involutional linear operator on a vector space over a field. And did we figure this out at some point, that when you're doing the eigenvalue analysis for involutions, you don't need a whole lot of algebraic completeness or something like that? It just pretty much, let's see, or is there? Maybe
No,
there's a little
bit.
There's a little bit. Okay, but it's probably, I think it's going to work out somehow. Right. I think because because this is going to be, 2 is going to be invertible over the 3-element field. So that means that, I think that's one of the things that means that the involutions on vector spaces over this field automatically have a nice eigenvalue analysis. So just these two eigenvalues, 1 and -1, also known as 1 and 2.
Right. Okay.
But
what are you going to do? You're looking for the sub group on which this is.
For some strange reason, I'm going to take the skew eigenspace.
Okay. I don't know why, but okay.
Right, and that's right. I haven't really told you why yet, except that this really should remind you of stuff that we've done in some past weeks, where we were trying to classify Z mod 3 torsors in some way. So in fact, this, I did at some point describe this, pretty much this procedure, as a conjectural way of classifying the Z mod 3 torsors over a field, like over the rational field or something like that, or over the Gaussian rationals or something like that. But now I'm sort of applying that same conjecture, but instead over a field, and I'm applying it to this ring A, which is, more manageable, because it only has a few primes removed, which means that its GL1 is slightly interesting, but not excessively interesting. So can we try to calculate what this group actually is?
Yes.
So you said yes? Is that what you said?
Yes, we can try.
Oh, yes, we can try. I thought that you had a guess already.
No. Let's do it.
So okay. So do you have any suggestions, or should I try to make suggestions? Let's see. So what are we trying to say? Yeah,
so is it too boring to first figure out GL1A and then think about GL1A tensor the Eisensteins? The first one may not help that much, but I just feel like I want to do it.
Sure, let's do that. Yeah, let's do that. Let's do that. I was worried that it wouldn't be excessively boring. I was worried that it'd be excessively difficult or something like that. But maybe you're right that it's not difficult.
Oh, boring. Yeah. So, well, I was thinking, since we're only inverting a few things, the GL1A should be something like all the numbers that are just like powers of 3 times powers of 7
times powers of -1.
3. Oh yeah, right.
So yeah, now it really is seeming like, right, that there is this third prime there, and it really does seem like Conway's -1.
Right. Yeah. That's right.
I don't know to what extent that's going to persist in the whole philosophy, but it sort of seems like it's happening here. And it's kind
That's
of a
on
weird prime.
they should have put the third pole at the third point at -1. Instead of
Is that the same -1?
I don't know. I'm
I
just
don't
joking. I don't want to try to figure that
know.
out.
Sure.
So, okay. So plus or minus 2 to the m, 7 to the n, 2 to the a, 7 to the b. So I think that's what we did.
Yeah.
So that wasn't too bad.
Yeah, so it sounds like you're saying that it's Z, direct sum Z mod 2.
Yep.
Okay. Is that right? Is that really what we're saying? I guess that's really what we're saying.
Okay. So let's look at tensoring it with the Eisensteins. Tensoring A with the Eisensteins. So now.
Well, no, I wasn't.
Oh, you're going to
try instead of doing this tensoring. Let's just experiment with throwing in this other tensoring here.
Okay, well that's even easier. Yeah.
So then we just that's going to kill off the Z mod 2. Let's see.
Yep, and then it turns the Z's into Z mod 3s, I guess. So we just
which coincidentally is that thing that I said was the final answer, which is two-dimensional vector space over the 3-element field. But in some sense, I think that is a coincidence. So I think you're right that we should now go back and worry about this other tensoring.
Okay.
So now what's going on?
So just a dumb guess as to what the invertible elements of A tensor the Eisenstein integers.
Yeah.
Is that, I mean, this is maybe neglecting some sneaky stuff that happens, but
yeah,
dumb guess would be that like you look at the Eisenstein units, of which there are Eisenstein integer units, of which there are 6, these 6 roots of unity. And
you're going to throw that in as a factor, or?
Yeah, I guess I'm going to take that old Z mod 2 that you had been talking about and replace it with Z mod 6.
Yeah, so, which if we want to, by Chinese remainder theorem or by something, we can also, break that up. It's like this.
Right. So I'm going to guess we get like that.
Yeah.
Plus these 2 Z factors relating to the powers of 3 and 7.
Well, so, okay. But one thing that's going to happen is, we're going to have to think about how 3 and 7 factor in the Eisenstein integer.
Okay, I knew there's going to be something hard.
So 7 is going to be, have I got this right? Is, you always have to check this for me, but it's like 7 equals 1 plus. So I'm calling W my name for the favorite primitive. It's what I call 1 to the 1/3 or something. Favorite primitive cube root of unity.
Yeah.
So I think 7 factorizes as 1 plus 3W times 1 plus 3 times the conjugate of W, which would be W squared. Can we just both try and check and see if I got the signs right here? Does this seem correct?
Okay. Let's check.
So that's equal to 1. Plus
9.
Plus 9.
Then 3W and 3W squared. W plus W squared is -1.
Yes, that's right, because the sum of all 3 of them is 0. So yes. So, they balance out. So the sum of any 2 of them gives the negative of the third.
Yep.
So it's
with -6 in the middle there.
-6?
Oh, sorry, -3. Sorry. Yep.
-3, yes.
Okay.
And so that seems to be correct.
Good.
So
okay, what the hell's going on? So if
yeah,
you're inverting 7, does that mean? Okay, that does not mean you're inverting both of those. You're inverting one of them relative to the other or something like that.
no, I think you're wrong. I think it
Oh,
does mean. I think whenever you invert a product, all of its factors, just think about it. Well,
okay.
tell me if I'm correct. That when you invert a product, in a commutative situation, if you're inverting a product,
Yeah, okay. Yeah,
every factor is inverted too.
yeah, I see how to, I mean, I can see the long explanation of why, but I don't want to say it. Yeah. Yeah, okay. So
Um,
okay, you're right. Good. Well, I guess that's good. So I don't know. It means there's more stuff to running around. So
right, right, right. But I think it's going to be, I think it's going to be like, give and take away or something like that, right? Because we're going to end up taking just an eigenspace. So it sounds like we've now got, it sounds like we've got this Z mod 3 over here, which, by the way, I think this Z mod 3 over here is actually what's associated with the prime 3. I don't even want to think about it because I think 3 is probably ramified. Is it ramified? I don't know. I think it probably is ramified. But I'm not going to worry about it. But I think it is. I think 3 is somehow ramified here, or there's something very funny about the prime 3 here. And it might be that it's ramified over the Eisenstein integers or something like that. But I think that's right. I think that's right. I think it might remember we were saying before that all the quadratic fields, or a whole, like half of them or something, half of the quadratic fields tend to be ramified at 2. And I think like something like a third of all the cubic fields or something like that. A third of all the abelian cubic fields are ramified at, or maybe 2/3 of them or something like that, are ramified at 3 or something like that. I think this ramification at 3 that I think is going on here, it's probably analogous to that ramification at 2 that happened for the quadratic fields, for a lot of the quadratic fields.
I don't
know.
what does that have to do with the
Yeah.
units group having this Z mod 3 in it? You're saying there's like some connection between the units group and the ramification. That
Yes.
sounds, is that something implicit?
Yes. But okay. Yes. But maybe you'll have to see how that works as we keep on going here. So, so let's try to proceed here. So what am I trying to say? Well, I mean, so one of the things I'm saying, I don't think we get anything else from, I don't think 3 is going to factorize and give us anything like that, but I mean, what are you claiming? You're claiming that
What are you claiming?
all right, it sounds like you're saying we've got these 3 from the units thing, and then we've got the 3 coming from the prime 3, and then we've got 9 coming from the prime 7. So that makes it sound like it's a 4-dimensional vector space over the 3-element field. But I think it's only a 3-dimensional vector space over the 3-element field. And I think it's because this little 3 over here is the same as the 3 coming from 3. I think it ends up being the same somehow.
I don't know. You're going too fast, too sloppy for me to keep up.
Well, I mean, I am going to keep on being sloppy here, but we're supposed to be okay with that. I mean, we'll try to be less sloppy next time, but for now we're going to be a little bit sloppy here. But
can you tell me why you're so set on the answer coming out to be two-dimensional vector space over F3. Sounds like you had some other reason why you were suspecting that would.
Yes, yes. There's this other picture. There's this other picture where we're gonna get something like, what am I trying to say? It's gonna be let me try to draw another picture of the things here. Let's see. Right. So one of them is going to have to do with the cube root of 1, but that's the trivial, right? Because the cube root of 1. Pretend for a moment that we are already working over the Eisenstein integers, okay, right? We have tricks where you can go back and forth between treating the Eisenstein integers as just something you treat formally, or you can think of it as something that you've actually got. So if we're already over the Eisenstein integers, then the cube roots of unity are already there. So this represents the trivial Z mod 3 towards it. But then there's another one, which is the cube roots, right? I'm writing this as though it's well-defined, but sort of the whole point is actually that it's, it's got this Galois ambiguity in it. When you take a cube root, you're actually getting 3 different cube roots or something like that. So there's the cube root of W itself. And there's the cube root of W squared. And I think these actually end up being 3 distinct torsors, 3 non-equivalent torsors. So one is, just the trivial one. We can call it the cube roots of unity, but it's trivial. It might as well be, just 3 separate things that are all identifiable. But then there's the cube roots of W, so that'd be the 9th roots of unity. Let's see, am I saying that right? Yeah, that's well, it'd be some of the what?
3 of the 9th roots of unity, right?
3 of them, yes. And then there's these other 3 of them, the cube roots of the conjugate of W. So this actually ends up being 3 distinct Z mod 3 torsors. And then there's going to be another one, which is the cube roots of the cube roots of 7 times the I just need a letter name here for this number 1. Remember, we had the prime factor of 7 was 1 plus 3W. I just need a name for this. Let me call it K for now.
Okay.
So we have the cube root of K times the norm of K. I need some symbol for the norm of K. This is the Eisenstein norm of K or something like that. Maybe I can call it like that or something like that. And then there's one here, which is the cube root of, or the cube roots of K squared times the norm of K squared. And then there's, other things like that here too. Right, and and the norm is also there with the W's, but the norms of all the W's are 1, so you don't see the norms there. But like over here, there's like
why do you stick these norms in there? I don't follow any of this.
Well, right. I mean, I at this point, This is dropped out of thin air, but this is what we're going to prove. We're going to prove that these 9 torsors forming this 2-dimensional vector space over over this field, over this 3-element field, is going to be the complete classification of all the Z mod 3 torsors over this ring A. So and right, this is right. So this is also going to be a certain cohomology group. And in fact, it's probably going to be at least 2 different cohomology groups, which for some semi-mysterious reason end up being isomorphic. So, you know, this guy that I learned class field theory from, to the extent that I ever did learn class field theory, this guy B.F. Wyman, he talks about this. He talks about viewing the Artin reciprocity theorem as, you know, in a sort of very technical, mysterious way that he tries to elucidate in a much less mysterious way. But he talks about it as being, you know, being expressed in this very inscrutable way as an isomorphism between cohomology groups. So that's one of the things we're talking about here. There's this little cohomology group. Maybe it's like an étale cohomology group or something like that. But that's one of the pictures that we're going to have here. You know, there's this little 2-dimensional vector space over the 3-element field, and we're going to see it as a cohomology group in various ways, but it's also classifying the torsors. And right, that makes perfect sense, right? You always expect, or you very often expect, torsors to be classified by a cohomology group, and it's probably exactly the cohomology group that you're expecting here.
Yep, that's good.
So yeah, we're trying to bring to, you know, we're probably going to try to wrap up really soon today. But we are planning out how we're going to understand this classification in a very multifaceted way with multiple very nice pictures and then nice ways of connecting the various pictures. And so I just want to say that, you know, this one in the middle would be the cube roots of k times w times the norm of k times w, or something like that. And that's what this whole thing is going to be. So do you see what I'm saying? This, right? I'm not explaining why it is this way, but I'm claiming that this is going to be a very explicit classification of these torsors. So each one of these is going to give us a special commutative Frobenius algebra over this ring A. And these are going to be, this is going to be a complete classification of all of those special commutative Frobenius algebras that have this nice action by Z mod 3 on them. And, you know, so, you know, presumably these operations of these Frobenius algebras are going to have, you know, in various places, factors of 3 and 7, 3 and or 7 in the denominator. And that's, you know, that's the legal limit for this problem. That's the only thing you're allowed to have in the denominator, you know. And so that's what's that's you know, I'm claiming that that's going to be the situation. I'm claiming that that's going to be the situation. You know, I'm claiming that this is going to be the classification of the torsors, and I'm giving these torsors to you very explicitly. You know, it's these special commutative Frobenius algebras.
I don't know which these ones are, though.
It's like, you know, adjoining the roots of these, adjoining these cube roots to the original ring A. Each of those is going to give us a special commutative Frobenius algebra, and not just a plain old special commutative Frobenius algebra, but one that has this nice action by Z mod 3 on it. That's going to make it into a Z mod 3 torsor. So one of the ad hoc things I'm saying here is that, you know, we're going to think of these Z mod 3 torsors as being these special commutative Frobenius algebras with a little bit of extra, this Z mod 3 action. But that's still a bit ad hoc, but it's you know, It's making some sense. And so this is going to be a complete classification. And the way this is going to work is that these ones right here are the ones that are unramified except at 3. These ones over here are going to be the ones that are, well, I might have drawn the wrong axis, right? There's part of what we have to figure out is, did I draw it correctly? I think it's actually, we're going to redraw it with instead of taking this as the second basis element, it's one of these other 6 that's going to be the second basis element. And I couldn't tell you right this second because we're running out of time. But there is going to be an arrangement here. We're going to arrange it so that, so that we're going to have the ones that are only ramified at 3 right there, and the ones that are only ramified at 7 are going to be there. And this other viewpoint on what ramification means is that it's about the periodicity of the splitting pattern, right? So that's how this other naive picture in terms of all this stuff about GL1. Where is the picture here? We started thinking about GL1 and everything. This GL1 thing that we're talking about here is working out what the possible splitting patterns, or really what the possible Frobenius patterns are, right? The Frobenius pattern is where you don't just say splits or doesn't split, but you also say, you give the extra orientation bit when it doesn't split. Again, it's like having a covering space with a fiber of size 3, and there's this, in addition to knowing whether it's split or non-split, you want to have this orientation on the fiber, and that gives this Frobenius pattern. And the possible Frobenius pattern is the way the reciprocity law works. It's going to be in terms of it's going to be in terms of the congruence properties modulo 3 and modulo 7. So right, that's what we're trying to work out here. We're trying to work out a way to organize all the possible congruence patterns modulo 3 and modulo 7 for these Z mod 3 torsors. So they're all going to look like, homomorphisms from the multiplicative group into Z mod 3 or something like that. And that's the way it's going to go. So, but I'm suggesting that now this is, I'm suggesting that if you're not, I'm suggesting that if you're happy quitting here, that this might be a good place to quit. But you have to be really happy. You can't just say, "Oh yeah, I'm happy," and then go out the door. I mean,
yeah, I can't just be happy. I just can't be happy just to quit. You mean?
Well, I mean,
have to be happy.
You have to just a little. You have to pretend at least that you're following my plan here. Right? The plan here is that we're going to get this complete classification of the Z mod 3 torsors over this ring A. And it's going to be very instructive and very nice and very beautiful. And in particular, it's going to have these multiple pictures, some of which very explicitly tell us what the torsors are, others of which tell us the Frobenius patterns of these torsors. And then we're going to have very explicit rules for getting back and forth. And that's this sort of isomorphism between cohomology groups. So we're gonna. This is the plan, but I'm hoping you. We are going to quit now, but I'm hoping you really are seeing you're getting some idea of what's going on here. That we really are dealing with these special commutative Frobenius algebras. They are actually very restricted over this ring A because we've only introduced a few reciprocals of just a very few primes. And that's keeping things manageable in terms of classifying the Z mod 3 torsors. And so...
Well, one thing I'm wondering is, to what extent are you saying special commutative Frobenius algebras just to humor me? Because it seems like you could be just talking about Z mod 3 torsors, right? If you wanted to.
It's more like humoring myself than like humoring you. It's
Like he's interested in special commutative Frobenius algebras, so now I'm going to take advantage of the fact that these Z mod 3 torsors are
well,
automatically special commutative Frobenius algebras to keep calling them special commutative Frobenius.
no, one of the things we really want to do is we really want to explicitly look at these at these co-pairing operations, or there are other operations we could use, but it seems convenient to use the co-pairing operation for special commutative Frobenius algebra. And we really want to see how, you know, that co-pairing operation becomes ill-defined, you know, depending on whether you've thrown in enough reciprocals or not. And that's really supposed to connect with, you know, other ways of thinking about ramification. And
okay,
you know,
yeah.
so we really do want to, I think we really do want to, and it's bad that I didn't do it today, but we really do want to explicitly calculate some of these co-pairing operations to really see, you know, where they fail. You know, when there is ramification.
Yep. Yeah, that would
unless you deliberately go out of your way to kill off the complainer, to, you know, put in the reciprocal of the primes at which there is ramification. So I'm hoping, yeah, now I'm hoping that we, you know, now you can make me happy by being happy with it.
Yeah, I'm getting happy. I mean, I just have millions of questions, but I think I'll wait.
Yeah, that seems like a good idea, because either you can give better questions, better answers to the questions. You could give better questions if we think about it for a while. All right, so thanks a lot. And
yeah, cool.
Okay.
Okay, we can try to do this next week. Well, let me end the recording.
Yeah, well, yeah, we'll have to figure out when the next meeting is.
Do that.